Welcome students to another session. Let us talk about this electron emission from a conductor. Now see this diagram. An electron conductor can be a negatively charged conductor or a positively charged conductor. The charges are distributed uniformly across the surface of the conductor. Now the reason being that, let us say a conductor is positively charged. The charges cannot be distributed inside the conductor because as per Coulomb's law, you know that there will be mutual repulsion between like charges and attraction between the unlike charges. So if let us say it is a positively charged conductor, so there will be a huge amount of repulsion between the charges. So they will try to arrange themselves at a very large distance from each other. So the best part of the conductor is the surface of the conductor. In this diagram I have shown the negatively charged conductor, and the negative charges are distributed on the surface, and this distribution is uniform. Now here we need to understand a point, that in electron emission we are trying to knock off these electrons from the conductor. Why are we trying to knock off this? Because the movement of electrons is basically the current formation. Okay, look at this diagram. I am just taking an example. Let us say this electron which is attached to the conductor requires 21 joules of energy to be released. Okay, now I have taken some scenarios. I supply 18 joules of energy. Will it be knocked off? No. 19, 20, even at 21 they will start to move. Exactly when I apply 21.1 joules, they will be starting to move away from the conductor. Now this 21 joules in this example is defined as the work function of that particular metal. Now work function of a metal is defined as the minimum amount of energy required for these electrons to cross the surface barrier, which is the metal. Okay, now it is given by this expression W is equal to H mu naught, where H is the Planck's constant. Its value is 6.6 into 10 to the power of minus 34 joule seconds, and mu naught is called the threshold frequency. See, basically this work done by an object converts into the energy. I told you in the previous class that work and energy basically are two sides of the same coin. Sometimes we use energy, sometimes we use work. The work done by an object in moving from one place to another is stored inside that body as a potential energy, I told you. Okay, so work function definition gives us an idea that how much energy is required to knock off those electrons from the external surface of a charged conductor. See, if the conductor is not charged, there is no question of any knocking off of electrons, no question of any work function. Only if the conductor is charged, you talk about work function. Okay, most of the metals have a work function between 2 to 6 electron volts. 1 electron volt is equal to 1.6 into 10 to the power of minus 19 joules. These electron volts are small unit of energy. Okay, so this is the process that is involved in electron emission. We will now see different type of electron emissions which are normally in use. Okay, yeah. Now first let us understand why we are trying to remove these electrons. In the chapter this direct current, what we have done, we have taken a battery and we have connected that to a resistor, and the charges were flowing from negative terminal to the positive terminal, which we are calling it as current. Okay, for the sign convention we take from positive to negative, but electrons will flow from negative terminal to the positive terminal. What is happening there? The extra electrons are moving from one side of the battery to another side of the battery. Exactly the same thing is happening here. See, now these charge conductors have more number of electrons. Now those have to be knocked out, and when they are knocked out, they will travel. So this movement of electrons as a beam is called a new type of a current, which is called photoelectric current. Now to emit these electrons, the first process is called thermionic emission. It's like this. You take this conductor and heat it. When you heat it, what will happen? The kinetic energy of the particles will increase. When the kinetic energy of the particles increase, they will naturally try to leave the surface barrier and move. An analogy can be, you take a water in a beaker, and initially the water is still. When you supply heat energy, what happens? The particles will move randomly at a fast pace up and down. That happened because you supplied heat energy to the water, which increased the kinetic energy of the particles which are inside the beaker. Exactly the same process happens here. So when the kinetic energy of the particles is increased, which is electrons here, they try to move away. Now this type of emission is called thermionic emission. In some of the cases it is used. One example is vacuum tubes. Okay, vacuum tubes extensively used the process of thermionic emission. Now let us move on to the next type of emission, which is called photoelectric emission. You see, this Einstein got Nobel Prize for this type of emission only, detection of this type of emission. Basically what he says, you look at this diagram. Okay, now this is a charged conductor. Now there is an incident light which has been shown in the diagram. The negative side is called the cathode and the positive side is called the anode. Now this energy which you are supplying, the incident light which you are supplying to these to this charged conductor, even they carry energy. Basically light consists of photons, and photons means packets of energy. Every light has energy. Okay, now every light has a different frequency, and the energy of the light we have seen in the previous chapter is given by the expression E is equal to h nu. So when the energy supplied by the light is more than the work function of the metal, what will happen means it will knock off these electrons, and these knocked off electrons will try to move towards the positive plate, which is the anode here. In another terminology, this negative plate is also called the emitter plate because it is emitting electrons, and the positive terminal is called as a collector plate. Now this collector plate terminal can be kept positive or negative. I will explain you why it can be kept positive or negative in the coming discussion. Here we are seeing only the type of emission. One more type of emission is called field emission. In this what they do is, like I have shown in the diagram, they take a metal plate. Now this metal plate is already charged. That means it has more number of negative charges available on it, more number of electrons. What they do is they connect it to a battery, a high tension battery, and you can see in the diagram there is a positive and a negative terminal. A huge amount of potential difference is created between the terminals. Now this potential difference, what basically does is it helps the electron move from the lower potential to the higher potential. We have seen an expression for this. Remember, we have seen in the chapter that U is the potential energy. It is given by U is equal to VQ, where V is the potential and Q is the charge associated. Now this huge amount of potential difference is what making the electrons move from one terminal to another terminal. So in this process light is emitted also. Now this type of emission is called field emission. So basically the idea is you have to knock off these electrons. The way you want to do it is your choice. So sometimes it is done by supplying heat energy, sometimes it is done by the field emission, and sometimes photoelectric emission is done. In your mobile phones, the flash that you see is an example of photoelectric emission. Okay, and actually most of the people don't know that this Einstein got this Nobel Prize for detecting this photoelectric emission and not for the expression E is equal to mc square. Okay, now let us try to understand this whole scenario with a simple example. Let us say some electrons are associated with a charged conductor, and 20 joules of energy is required to knock them off. I am just taking a random example just to explain. Let us say the supplied energy is 22 joules. So 22 minus 20 is equal to 2 joules. So what is 22? 22 is the supplied energy. 20 is what? The work function of the metal. So 22 minus 20, you are getting 2 joules. What happened? When you supply energy to these electrons and this energy is more than the work function, what will happen? The electrons will be knocked off. So that which is knocked off, it will try to move and it will gain kinetic energy. So in this expression, this 22 is equivalent of h nu. 20 is equivalent of h nu naught, and the 2 joules is equivalent of half mv square. Okay, that is the kinetic energy. So our expression is E is equal to W of phi plus half mv square. Now this is the Einstein's equation. E is equal to W of phi plus half mv square. Now here if you see, this work function is a constant. So if you are increasing the energy, what will happen? The velocity of the electron which is emitted from the conductor will increase, and at some point of time it will attain its maximum. Okay, so energy is increased, velocity is gradually increased, and it attains the maximum velocity. Now let us discuss the important point that using photoelectric emission, you provided a incident light. Now the energy associated with the incident light is more than the work function. The electrons were knocked off from the charged conductor and they started moving and they gained kinetic energy. Very good. Till then everything fine. And because this electron, if you connect this in a circuit, what will happen? These electrons will be moving like a beam, and this current is called photoelectric current. Excellent. Now how to stop this current? Suppose it is a DC circuit, a direct current circuit. What you will do? You will simply remove the battery. The flow of electrons will stop. But here the process is not so easy. Here what is happening is, this is happening automatically, isn't it? So what basically is done is, this anode plate which is called the collector plate, you reverse the polarity. That is, initially the collector plate was positively charged. Now you reverse the polarity. There is an option available, and when you do it a negatively charged plate, these electrons which are moving towards the collector plate, what will happen? There will be mutual repulsion now. Even in that situation, the electrons that have been knocked off from the charged conductor and which are moving at a high speed towards this collector plate, they will experience repulsion. Some electrons will still go to the collector plate, but the weaker electrons, they will be stopped, and they won't be stopped in just a flash of a time. Slowly they will die down. Okay, now this potential which is acting in reverse to stop these flowing electrons is called the stopping potential. So this is an important step in creation of this photoelectric current. Here what happens is, remember very carefully, this collector plate polarity is reversed, and this is reversed only to stop the additional flow of electrons from the emitter plate. Okay, so in this situation what happens is, let us say that stopping potential is V0. So what is the work done by the stopping potential? You know that U is equal to VQ, and here charge is the charge of electron, which is E. So EV0. Now this much amount of energy is done by the charged terminals, and here I told you that some electrons which have got low speed, they will not reach up to the collector plate. but a particular electron will be there which has got sufficient speed and it will be collected in the collector plate. Let us say that speed, which is the maximum speed, is Vmax. So EV0 is equal to half mv max square. That is the energy supplied by the terminals. It has been used to do the work, and that work is done by the kinetic energy of the moving electrons. Any question comes on this potential, stopping potential, you should remember how I have written this expression. EV0 is equal to half V max square, half mv max square. If you observe here, there is no mention of work function in this equation. There is no mention of work function in this equation. Now here many questions related to graph are often tested. Some of the graphs I want to discuss with you. The first graph which I have shown in this diagram is between the photocurrent and the potential, the stopping potential. The x-axis, which is also called the independent axis, is showing the stopping potential, and the y-axis is photocurrent. If you see here in the figure, I1, I2, I3 are the intensity of light. See students, here intensity of light and current are totally two different things. Okay, so here we are subjecting this charged conductor to different intensity of light. Okay, different luminosity. So when they plotted this graph, see on the left hand side, on the negative side of the terminal, for all these three different intensities, the stopping potential value is same only. You can see it is a negative value. Let me just write it over here. In this diagram, now I am talking about this. This is your stopping potential, and this stopping potential is independent of intensity of light. Whether the light has got more intensity or less intensity, it is not going to change the stopping potential value. So this is one point. Now, while having a discussion about this stopping potential in the previous page, if you observe here, I told you that when you change the polarity of the collector plate, these moving electrons, couple of electrons will still be collected in the collector plate. What about the rest? They will not be. So that means even though you are applying the stopping potential, all these electrons will not have the constant speed. Some will have more, some will have less. So this is also one more point which can be understood by this graph. Okay, so you can note on this point that stopping potential is independent of intensity of light. Okay, the second graph what I have shown is between the intensity of light and the frequency. I told you that there is a frequency associated with the work function of the metal, and that frequency is called the threshold frequency. If you plot this graph and observe this graph, you will see that photoelectric current is increasing by the intensity of incident light. See, when you increase the intensity of light, the stopping potential is not affected. However, this photoelectric current, that will increase, and that is depicted by this graph. So remember this shape. Why more current will be generated? When you increase the intensity of light, basically you are supplying more energy, and that more energy is knocking off more charged particles. Because more charged particles are emitted, more amount of current will be generated. That is the reason. So you should remember that photoelectric current is directly proportional to intensity of incident light. Let us move to the next graph. Now this graph is between on the y-axis you have photoelectric current, and on the x-axis you have potential. Now here what we have done is we have chosen three different types of lights. Obviously every light has an associated frequency. mu3 is more than mu2 is more than mu1. One thing was observed here. The saturated current value for all these three currents is same. However, the stopping potential for individual lights is different as shown in the diagram. For the first light it is V01, for the second one it is V02, and for the third one it is V03. What do I mean by saturated current? When you try to create this photoelectric current, you try to increase the you try to release more and more electrons from the charged conductor, and this energy initially should be more than the work function of the metal. Now after that, when you still increase the energy value, let us say, let me go back to this example, the first example which I was discussing. Yeah, it is here. Look at this example. Here 20 is the work function of the metal, 22 is the supplied energy. You can put 24, you can put 26, you can put 50. Simply if you keep on increasing this energy, more amount of electrons won't be emitted. Okay, so there is an upper limit for the electrons to be emitted. Now that upper limit is called saturated current. So in this situation, all these three lights of different frequencies and wavelengths, they are giving same amount of saturated current. However, their individual stopping potential values are different. That is what this graph indicates. So you can note on this point that saturation current is independent of frequency. So three important points I have discussed. These are the three rules you should understand in photoelectric current. See students, the graphs which I have discussed, they are often tested in JEE Advanced. So you should better know this shape of these graphs and why the shape is like that. Often many questions are asked on this. So let me move to the final graph. Now this graph is between stopping potential V0, which is on the y-axis, and on the x-axis we are taking frequency. If you observe carefully here, on the x-axis and y-axis, I am repeating and changing the parameters in a particular pattern. Okay, in most of the graphs on the x-axis, either you have potential or you have frequency. Only the y-axis is changing. You need to observe that. Okay, now what is the shape of this graph? Let us go back to the Einstein equation. Einstein equation was h nu is equal to phi plus ev. What is phi? Phi is the work function, ev is the work done. Okay, because of this you have because of this collector plate terminal which you got reversed. So here, because we are plotting a graph for the potential, so I can write v is equal to h nu by e minus phi by e, dividing both sides with e. So finally you are getting this expression. This expression is resembling this y is equal to mx plus c. Okay, now how to find the intercept? Put x is equal to 0 in that equation. Here you have to put mu is equal to 0, because mu, you are plotting a graph between v and mu. So mu is the independent variable. You have to put mu is equal to 0. You will see that v is equal to minus phi by e. Now look at this graph. Now this graph is a straight line, and this dotted line is what is the, if you extend it backwards, so you are going to get the value of v0. Okay, it is a negative value in the graph. See, y in the upward direction is positive, in the downward direction it is negative. Same is what you are getting from the expression. So that value which it is going to hit on the x-axis, that is called threshold frequency. So often if you want to find the threshold frequency of a charged conductor, this method is adopted. You will use different energies and you will work out this graph, and wherever the graph crosses the x-axis, that value is your threshold frequency. Some of the concepts I will discuss in the next class. Meanwhile, I'm just sharing this. You make a note of all these points. Till then, take care. Bye bye.